when you say that you want to learn large language models, there are three words specifically. Uh, One is large, one is language, and one is model. So naturally, these three words, each of the R, 3 R's, will be correspondent to the first R will be dedicated to understanding what is language. You have understood tokens, but again, it's my duty to talk bit about it again. Then it will be about the next 1 hour, it'll be about language modeling. What is language model? And finally, the last 1 hour, it will be about what is large language. Okay. Um, the dynamics of the class will be feel free to stop me anytime, ask questions. If you do not ask questions, this will probably end in 1 hour or 1.5 hours or 2 hours. But if you ask questions, there is an opportunity for both of us to interact and learn and utilize another hour or so for your own benefit. I will not be covering in the large part that you see here too many things because that will be a waste of time, I believe. However, I will be covering the most important aspect of self-supervised learning and the large-scale pre-training, which I believe is very foundational to the large language modeling aspect. That how do people take care of the large aspect of the language modeling? So, any questions out here? Do you want me to address? I know we didn't start, but any questions you have? Okay.
Srijit, one question.
Yes. Go ahead, Ravini.
Irrespective of these LLM models, the tokenization mechanism remains same across all the LLMs, or will it differ from each LLM to LLM?
Yes, so the tokenization, yes, interestingly, you all have been exposed to tokenization. I don't know how it has been exposed to you, but or you have exposed yourself, but tokenization often is corresponding to a model, but it's independent. Like the mathematics of tokenization is simple. You have
Mm.
language, okay?
Mm.
Let's say Pavani. Pavani is a name, and there is another name called Pavan, right?
Mm.
So how do you mathematically transform this um, into mathematical vectors, let's say? That's the basic problem. Defining the function from the set of all collection of all words or language fundamental atoms of language, you can take anything. You can call it characters also,
Okay.
but to a mathematical framework. Now, different large GPTs or different large language models do it in different ways that's associated with it.
Mm.
Um, for example, as far as I remember, GPT uses a specific method called byte pair encoding, if I'm not wrong. Um, there are many other methods like that. Now, whether you will, so what type you, so the question is that when you want to convert this, and I want to connect with the first point that what is language, when you want
Mm.
to convert this words or characters or the atoms of language into mathematics, what properties you want to retain? Like, for example, we can do it in alphabetical order, just like it's in a dictionary. We can do it in alphabetical order. For the first word in the dictionary, we can name it zero. For the second word, we can name it one, right? That's one of the ways, right?
Yes.
But we will not do it. It's bad. It's not a good way because we are losing everything about the language.
Mm.
Only mathematics is remaining. That's what we do not want. So, taking your question as a source of inspiration, I will be moving ahead to understanding that what exactly is language. Does it make sense what we discussed, Pavani?
Yes,
Or you have
yes.
any follow-up question?
Yes, yes,
Okay,
Srijit.
okay. Any other questions from anyone? Okay. So
Sir,
again, what is language? Yes.
yeah,
Sorry.
sorry
Yes,
to
Sean.
disturb you, sir. Sir,
No,
actually,
no.
it will be helpful, sir, if you kindly explain what is called model and how it is developed actually, sir.
No, that will be the second part.
Okay,
Uh,
okay,
so,
okay.
yeah.
Thank you. Thank
First, we will understand what is language, because the whole idea of large language model, the very first step, like you have probably have done linear regression. The very first step is to have the data in mathematical format. The hardest part about language or image, still image has a mathematical representation, but having a mathematical representation of something raw data like language is very hard. Um, and that has been a long research point of interest. So we will understand first of all what is language, what is the mathematics of language. That's the first R's goal. Okay, I hope all of you are ready for this. Okay, so what is language? So again, we have said that we are seeking to understand, seeking the understanding of what is the mathematics of language. And to understand that, let's take this example. Let's say, um, and as Shondip has said, to understand what's the mathematics of language, we will just take the framework of what is language modeling, and based on that, we will understand. Okay. So the language, what is the definition of language modeling? The definition of language modeling is simple. That the problem statement is the following: that given a sequence of words, this is what language modeling means, guys. Given a sequence of words, let's say, as you can see, I will meet you at D, and then your keyboard will give you a few options: the cafe, airport, office, etc., etc. So given a sequence of words, what is the next word? Okay. So this is the basic problem statement. Okay. Any questions? Okay. So this is what is the meaning of language modeling. So now coming back to what is language, language has very two important information, guys. Okay. One is the semantic meaning of language and the positional meaning of language. For example, so let's try to do this simple exercise, and I want everyone, each different person to, um, participate. So let's say there's this line called Srijit loves to, and then dash. Now in this dash, you have to fill up these words, right? Now let's try to do this. So why or why not? So can we put barking here? So Srijit loves to barking. Can we put that? Yes or no? Any idea? Why?
No.
Why is that, Shundip?
Actually, Sijit is a human being, sir. So,
Exactly. It's not a
yeah,
dog. And
yes.
anything
Uh,
else? So bark would have been possible?
no, that is also.
It's not a possible feature for a human being.
Sorry, Rahul.
I think it's not a possible feature for a human being barking.
Yes, barking is okay. But is there anything else? Grammatically incorrect. Very good, Shreya. So there are two aspects here, guys. One is I am not a dog. So the feature of barking or bark cannot be associated with Srijit. But there's also another aspect, as Shreya has mentioned, is it's also not positionally possible.
Okay, sir.
Okay.
Hmm.
That the barking, the ing is also preventing that. Okay. So yes, so barking also preventing that. So there is a two. I hope you're taking down notes. So there are two concepts out here. One is the information, the connection between the understanding of what the word means with respect to the other words out there, and also the positional information of a certain word. Okay, let's go to the next one. Swim. So can it be? So is it possible here to do the swim thing?
Yes,
Why is that so?
it is semantically and positionally correct. It appears.
Very good. So, okay, good. So, what about the next one? Play cricket? Can we do that?
Yes, sir.
Same thing. that it has semantic meaning, and it can be, it's positionally possible. Think deeply. Is it possible?
The next word means one word has to come, right?
I mean, I'm just, you're right, Shopon, Mr. Nonde, yes. But I'm just giving examples of what is language here. But yes, it can be one word or two words. But yes, I'm putting out the understanding out here rather than being too very specific about how many words. Yeah. So it can also have think deeply, right? So it's positionally possible, semantically it's also. So semantic means meaning here, that meaning of the word, the relationship with respect to the meaning with the other words. And position means whether that word is possible out there, as you know, the I mean, in terms of, as you said, grammar. Okay. So can it be do math? So yes, so barking is semantically not possible, positionally not possible. Swimming is both positionally possible, semantically possible. Play cricket is the same. Think deeply is the same. Do math is the same. But again, coding is semantically possible, right? But positionally it's not possible. Does it make sense, everyone? All of you?
Yes, sir.
For example, eating deer is, it depends. I mean, to some people it can be semantically possible, to some people it may not be. But essentially, it's positionally not possible because eating is not. So again, this depends. As I said, I want to keep one ambiguous. It depends on the data, on which data it is trained. Okay. I am also here. It's positionally possible lay eggs, but semantically it's not possible. Right? Doesn't make sense, guys? All of you? Any questions based on this? So what I wanted to make you understand here is that language, or every word, is not alone. Its representation should come from the fact, its representation should come from the relationship with the other words. Okay? And the relationship has two components. One is the meaning of the relationship, and position. And we must make sure, guys, that both of this are captured in the final vector representation, in the tokenization, as you say. It's very, very important. Both of them should be captured. Okay. So to remind you that what is tokenization? Tokenization is, as Pawan has asked, so you have a set of words. Let's say I'm writing a bit mathematically now, x1, x2, dot xn. The goal, so this is a set of words. The goal is to transform every word, it's a function, from this set of words to n-dimensional vectors. So every word should have its unique, very unique representation, vector representation, the mathematical representation. We'll see more examples, do not worry about that. So it's a vector. All of you are aware of what is a vector, right? Or, feel free to tell me. I will be explaining you. It's your job. You have paid for it. So you should ask for explanations from me. Does anyone need explanations of what is a vector? Feel free. Okay. So a vector is a set of numbers. Okay. Okay. And what I wanted to understand that this represent this function that we will build must have two of these components. It should somehow incorporate meaning component and the positional component. Okay. So let's go to the next idea. So to give you examples of position, let's understand that position can be long context length. Let's consider this sentence out here that Harrington is a person taught at Harvard University and the National War College. Okay. So this is a person and these two are organizations. And you can see that in this very sentence, the first word has a meaning to the last word. So the context, so the words, so this is an important thing for modeling, okay? I'm writing this down that words or language has large context length. Now, why am I very specifically speaking about this? Because this will be very important of understand. Our goal is to do language modeling. Now, what is modeling? The modeling is, as I said, that predicting the next word given a few words. We'll come to this again and again in the future into this discussion. But why am I specifically saying long context? So to tell you that, to make you understand that, okay, anyone has some idea? Anyone wants to put in their thoughts or about this? That why am I very specifically talking about long context? So a hint of direction of thought is there something with short context? Is there some data? Think in this format. What
It's
are
a
the language data,
kind,
right?
yeah, kind
Sorry.
of dependency, maybe, right? Let's say that particular word after a long length might have dependency on the very previous one in the beginning.
Yes, that is about language. But what I'm saying is that why am I specifically talking about large context? So is there any data that has short context that is very local, not very global in nature? Any ideas, guys? Any idea? Think. Is there any data where the data information are very local, not too much global, mostly local? Do you know of any such data? Any hint? Or any thought? Sorry, I've given you a hint. Any thought? I think people are writing in the. Okay, no one is writing. So any idea? No ideas. You've seen every day you are seeing so much data around you. So every moment is an information exposure to you. So what kind of data has very income data? Okay, income data. I mean, you mean stock data, stock market data, Shubhangi? Okay, stock data. I agree with that a bit. Yes. Yes, I agree with that. Anything else? Anything else? Inventory. What is that? Sorry, I'm not aware of that, Musabir. Sorry, Mubashir. What is inventory data? Okay, data collected for SIR purpose. Yes, okay. I mean, yes, you're right. but I don't think I mean, okay, so when I'm saying long context, you have to the data should be like, see, the data has the number and also there is a dimension to it. Okay, so let me, yeah, probably the question is not well posed. So I wanted to make you understand about image. Okay, so when you take an image, because we will use the same modeling for other purposes in the future, you will use it. So when you have an image, let's say there is a person out here and there is cloud, okay, and many other things. There is mountain. So it's very local. Let's say if you have a local, a 4x4 pixel out here, you will probably see all white around. I mean, all white, the same color around this cloud. Okay. So what I'm saying is that, and that's why it's very inherent in the modeling of the image data. So that's why I used convolution over there, the idea of convolution. Why am I saying this? Because you will not be restricted to learning AI for language only. You will be naturally asking about other methods. And convolution will come up as a natural choice because that has been there much before in the AI modeling industry for imaging. So natural question that should come to you is why not convolution for image data, for language data? The reason is this, that convolution is mostly for local context, short context. That's how it is built. But we cannot use that for language data because it's a large context, large. So for example, the sentence can be large. Let's say Harrington taught at Harvard University and he likes to eat strawberries, and then you can take a lot of everything, and then at the end then you can say, and also he taught at the National War College. So you can see that, and you don't have control over the data set. The data set is worldwide, so you do not know how the entire thing has been there. So that's very important, guys, to understand that language can have arbitrarily large context and relationships, because as I said, relationships is very fundamental to actually model this into tokens. Okay.
Can I ask a question here?
Yes, please,
Yeah.
Shubham.
So yeah, your image could also have the higher resolutions, and I mean, if you look at an image pixel, so image pixels probably like say the 1,000 by 1,000, so it could have the more than the character involved in the text, and also image could also be cat, dog. It have a large, huge database. So I mean, if you can more
Oh, no, no.
clarify.
So, okay. So when I say context, so you're right. So it's not in terms of number of data, but in terms of the feature space. So if you consider each image as a sequence of pixels, I'm considering in that format. Does it make sense?
It
Not
could have
in,
features
yes.
also, right? It is not the features could also be the now lot of features possibles in images.
Yeah, so you're right, absolutely. But it's not. So when you look at an image, what I'm saying is that the relationship are mostly found locally. Now you can make a synthetic image, let's say putting a lot of cats all over the place, okay? But that data is not always so often. It's very rare. That's what I'm saying. Does it make sense? So
Okay.
what I'm saying is that, right? Sorry?
In general, you were speaking that image have the local information. In general.
In general, mostly, yes.
In
But in
general.
language, you know, even in this simple language setup, so what I'm saying is that you can find people are finding a lot of success in image modeling using local context. Okay, it is on success. But when you do some thought experiment and ask the same question, that can I find the same success in language, the answer is no, because you do not have control over it. Does it make sense? That's what I'm saying. So it's
Okay.
most of like, you're right that I mean, yes, I mean, for example, if you have just a person's image, this pixel can be blue and this pixel can be blue of the sky, and they have long context, that's for sure. But you can extract most, but that is not important, what I'm saying here. That 2 pixels just focusing is not important, but here every pixel, rather every word is important. So the modeling should be changed or adapted to this data set. That's what I'm saying. Does it make sense, Shubhra? Very good question, actually.
Yes, yeah.
So it means you're thinking. That's what I like. Very good.
Yeah.
Any other questions, people? Any other questions? Great questions coming up. Okay.
Sir, I have a question, sir.
Yes.
Sir,
Please,
can
Sean.
you please kindly explain more on data, sir? Means what is called data and what are the types of data?
So data is information.
Okay.
Okay.
Hmm.
So you see, did you have a computer science background?
No, sir, I'm a mechanical engineer, sir.
Okay. So data is, just it will be a 2 minutes answer. So data is
Mm-hmm.
information. Okay.
Okay, sir.
Information is represented in bits in computer. Okay. Zeros
Right.
and ones. You're aware of
Hmm.
that, right?
Yes, yes.
Now then people thought that what data is mostly important. Then they went to the next stage using those bits.
Hmm.
They went to the next stage of integers or Boolean values, right? Int
Mm-hmm.
64, floating values. Why? Because these are easily available, right? These are
Hmm.
mostly used. And then people thought, okay, no, we need another level of hierarchy. They tried to combine these integers or floating values together into list, into arrays,
Hmm.
into sets, into dictionaries, JSON file, let's say.
Mm-hmm.
And then said, no, there are more hierarchies. Then they came up with n-dimensional arrays. Okay. The
Hmm.
images. So it's a hierarchy. Data is in hierarchy. Okay. So
Hmm.
it starts with bits. You combine them to get the most important what are used, and then you combine them, keep on combining them again. Okay. And then you have now data structures. Data structures and their corresponding realization as a object.
Hmm.
So you can also call therefore the contact, or let's say how the data of a student is saved in the entire database of a school. That's also data, right? So
Mm-hmm.
it's essentially starts from bits, and then it goes into different hierarchies of abstraction, which is called data structure. Okay, so that is
Mm-hmm.
data. So in this very specific case, the data structure is nothing but an arrays of strings.
Okay.
Strings are the words, let's say. Here it's a string. Okay. But if you go further into it, you can also call it bits, a sequence of bits. But what level of abstraction you want to talk about? Does this make sense, Shondeep?
Yes. So, sir, in that way, why means or how we can call any image as a data, sir?
Okay,
Means
very good
I
question.
am just trying to understand the mathematical representation of any
Yeah, so
data. Yeah.
ideally you should read more about it after
Yes,
going
sir.
back. But
Yes,
because
sir.
this answer
Yes.
will not satisfy,
Hmm.
a pixel is just every pixel. Let's say you have this, you have a circle, a black circle. So every pixel is, if you cut it up, every image is nothing but a matrix. Okay, let's take it a
Hmm.
grayscale image. It's a matrix, and every pixel,
Hmm.
if you go zoom into it, if you zoom into it, you will see something like this.
Hmm.
You will see something like uniformly colored. So that is a pixel. So each pixel is either has an intensity value of how much gray it is. Okay, it's a grayscale image. So essentially it turns out that every pixel is therefore a number, and usually this number is between 0 to 255. Okay, telling you
Hmm.
if
Hmm.
it's 0 then it's black, it's if it's
Hmm.
255 it's white. So it's a spectrum of values. So it becomes
Okay,
a
sir.
two-dimensional array. So it's a matrix.
Okay, sir.
That's it.
Thank
Does it
you,
make
sir.
sense?
Yes, sir.
Yeah.
Yes. Thanks.
Very good. Yeah, so what I'm saying is that these questions are very fundamental, and you should ask these questions to yourself, and then you should ask this question to ChatGPT or books and learn and make notes. Okay, this is very important. And this way of thinking and doing is very important, and I want to instill that habit a bit into you. Any questions more? Any more questions? As you can see, I am ready to go to the very fundamentals, provided it's in the framework what I'm discussing. Okay. Okay, very good. So we have understood that what language should mean ideally. Then we should go into think about components of language. What is, I already discussed a bit about it, but we will discuss more about it. What are the components of language? How to define a language? So the question that we're interested in is, how is a language defined? If you take any language, let's say you are learning a new language, okay? Let's say you're learning Chinese, okay? If you're learning the Chinese language, then you will first need to learn what are the very fundamental characters of Chinese, okay? And then you will need to learn what words are formed using those characters, okay? So the very fundamental of this language is this. Now, at what hierarchy you want to learn the pattern, that's very important. So there are characters. Okay. Let's say if you take English language, A, B, C, D, even a number is language. 0, 1, 2, 3, 4, 9. It's a language, right? Mathematics, like integer is a language. That's why even beats are language. Okay. The bits, zeros and ones. Now, why it's language? Because, I mean, the same modeling I will discuss. Did anyone hear about Claude Shannon? Anyone? So he is the very person, he is the very reason why he is the reason why why the system of communication could be built. That's the very reason why we could call each other a long distance. Okay. So, and this based on this person only, the Shannon's entropy. The entropy of something is, I mean, not entropy has been already been there for in statistical physics, but the entropy in terms of information. So he's a person who defined entropy of information, and he wrote a paper called A Mathematical Theory of Communication, which essentially changed the communication between human beings. Now, why I'm mentioning this? Because the very modeling he used in that paper, I forgot which year it was. Sorry, that's my error. I should have remembered. But the modeling he did there is the same modeling we will do for language in the next part. Because if you remember, second part is language model. We will do the modeling in this next part. The same model he did that there initially. So even bits a language, 0, 1s a language. It's sorry, it's the characters of which language is made up of. Okay. You can also define at the level of words abstraction. Let's say you can consider all the words in the dictionary. Okay. And that's also a sequence of words like I am, etc., etc. So a language, so it depends upon how you, at what granularity you want to represent the data set. That's the data set building part. So given that you are aware of the representation, given you know that what representation you want to talk at, the language is made up of this vocabulary, these fundamentals. This is called vocabulary. The fundamental building blocks, atoms of language. Does it make sense, everyone? Any questions?
Yes, yes.
Okay. So, as I said, this is a very fundamental atoms of language, these symbols. It's very important to remember this point, guys, that even 0, 1s are language. It's very fun. It's the basic vocabulary of any integer. If you want to represent in binary, if you want to represent in decimal, then these are the very fundamentals. Okay. Okay. So now let's understand this a bit. Okay. As I said, there are two concepts to learn in language of each of this XIs, or I called VIs there. One is semantic information and one is this positional information. So semantic information says that how are these XI semantically related? Again, I said it's a relationship. One word or one symbol doesn't stand alone. Its presence in respect to other symbols. So how are understand both the position and semantics are relationships. Okay, they are not standalone understanding. So therefore, how does this semantic relationship, how XIs are related, semantically related to others, and similarly how XIs are positionally related to others? These are the two main questions we want to measure. So I have this little picture over here. So the goal is what? The goal is to have these tokens, the fundamental atoms, let's say. So it loves to do math, let's say. And each of them has to be turned into a vector. Okay, that's the very goal of tokenization. All of you have understood that. Or not a tokenization. That's the very goal of vectorization, like embedding. So when I say position, you have to understand that position means that where this Srijit word lies, at which part of that language. For example, in this case, Srijit starts, it's the beginning. Okay, it will never be loves Srijit to do math, right? The noun should come first before the verb. Similarly here. So when I mean position, I mean the index. Position is the index of the word. Okay, let's call it a word. And when I say semantic, it's the individual binary relationship between each pair of words. For example, what is the relationship of Srijit to Srijit? Is there a relationship? What is the relationship between Srijit and loves? Srijit to two, Srijit to do. For example, there is a relationship ideally between Srijit and two. Okay, two comes before because there is loves, the word loves, so that's why two comes. The most of the relationship. So can someone tell me what is the most important relationship? Which word is most importantly related with Srijit? Anyone? Or multiple people? Not anyone. Any two, any three. Which math? Okay. Looks. Anything else? Yes, you're right, Shubhranshu and Vijit. Any other ideas? Yes, very good. Sridhi itself important, highest modes. Very good, Shreya Shuvangi. Swim. Where is swim coming? Did I have swim here? Probably you are referring to the previous one. Loves is also important because it's a human quality. Do is also important. Yes. But I would say Sridhi is the highest. Then comes loves and then math and then do. And two at the end. And similarly, you can do it for loves. For loves, any idea? Go ahead, I'm listening. What will be the two important words for loves? Important related words. Two, okay, two is important. Yes, it exists because loves has actually nothing to do with do and math, right? I mean, in this case, yes, but it will not be so important to, I mean, yeah, I mean, yes, in this case, yes. And what I'm saying is that Srijit loves and math. I mean, rather, yes, in some sense, if you want me to select only one, I would say Srijit and math is the most important here. I mean, apart from Srijit and Srijit. And think in this way, that which is very unique here and which is very different here. What information new is gained here? Loves always two. Yes, two is important here, but loves is general, so I would say loves to two is more important here. It's general. It's not um unusual. Again, two is do is also okay. So yeah, so when it's generic words like this, it's the usual relationship. But when it's important words like very unusual words like Srijit and math, it will be different. Okay. So yeah, what I want to do is we are explain rather is we are understanding binary relationship. So can we express this as a matrix to capture this global relationship, every word to every word? And you will see that the answer to this is the very fundamental thing that you always heard while learning large language model is this is exactly what attention does. The very mechanism of attention is to capture this relationship. Okay. And we will learn about what is attention in a bit. Doesn't make sense, everyone? Any questions out there? What I'm trying to train you is thinking in terms of position and this relation, this semantic relationship. Okay. Okay. So now let's assume that, so this is what we want, guys. Okay. We have not talked about that what we should, what we are doing, how we are actually modeling it. Okay. How we are transforming from the tokens to the vectors. We have not discussed that as of now. We will discuss that. What I'm saying is that should contain both the position and the semantic relationship. But let's say you have this vectors representation. Okay. How do you measure the similarity between these vectors? The semantic meaning. How do you understand the similarity between these two vectors? For example, and that is what cosine law does. For example, the very fact that, so let's take this example here. Let's say you have this vector called king. I'm understanding in 2 dimension. Okay. You have this vector called king, and you have this vector called queen, and the vector called noun, and a vector called woman. So if assume that these vectors encode the position, the semantic information between them. If the vectors encode the semantic information between them, then how should they capture it? What should be the relationship? The relationship should be king minus queen. When you subtract the king from the queen, the royalty from both the king and the queen is deleted. Right? So you can say in some sense that king, let me write here. So king is a man plus royalty. And the queen is a woman plus royalty. I think this was in terms of vectors, guys. So when you do king minus queen, you naturally delete the royalty from them. So you get man minus woman. This is the ideal case that will happen. This is the ideal case that will happen when this vector representations are semantic in nature. Right? All of you agree with this, guys? So we want to have this notion of semantic. So this is what I mean by semantic. This relationship should be there. And this should ideally look like this. King minus queen is man minus woman. The vector should be the same. Does it make sense, all of you? Yes or no? Can you write yes in the comment box? Any other? Okay, Sriyaza, how is the information entropy of information significant for language models? Do we make the matrix from the entropy of each? Oh, this one. No. It has nothing to do with information. Sorry, entropy. Entropy is, you should read more about this, Riya. You should read this book called, let me see. I have this book. No, I have it in my lab. Introduction to Information Theory. It's a very small book. It's like a very short book. Yeah, please ping me on LinkedIn and I will give it to you, okay? Or email me, anything works. I will share my email ID.
Yes, sir.
Tell me that I will, uh, yes, just email me that you want the book. It's in my lab desk. I forgot the. So it's a very small, short book. The whole idea is to understand entropy of information. So entropy is essentially how random information is. Like, if you remember when, uh, I don't know if you have seen that phase, but in previous TVs, when the network goes away, it's totally random, right? Like jig 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 jig, something like that. So that is what random is, and at that entropy is really high. When more structure comes up, the entropy reduces. Okay, that's why the entropy of really high heat molecules is high because they are random, but the entropy of a solidified ice is very low. Okay, so entropy is equal to measuring randomness. So how do you measure it? That's in the book, so you should learn about that. It's a very short book, and it has nothing to do with so entropy has entropy is not a binary relationship. Entropy is a like is just a singular relationship of a set of an object. Okay, so you do not need multiple things for entropy. Rather, entropy is a property of the probability distribution, to be very precise. Okay, Sriya, does it make sense? Okay. Any other questions? Okay. Any other question? So what is cosine similarity? So you need to measure the similarity between two vectors, and this is very important. The cosine similarity between two vectors is cos of the angle between them, even if it's in a high dimension. Okay. And the generalization of that is the dot product of those two vectors by the norm of those two vectors. This is the basic, uh, yeah, just dot product by the norm, and this is just cos theta. Okay, the angle between those two of them, those two vectors. And you know that if the angle is large, the cos theta, if you remember the graph of cos theta, it's this, right? So if the angle is large, the similarity value will decrease. And at this point, it becomes opposite. The angle becomes more than 90 degrees. So it's kind of opposite. So it's a perfect measure for similarity. Does it make sense, all of you? All good? Any questions? Okay. Yes. So we are almost close towards the end of the first half, and you can see it's almost 1 hour. Um, so as you probably have understood, vectors are the very fundamental of data, the math of data. And I think I forgot his name. He asked the what is the math of image. So it's very obvious here now. So it's the tensors. Okay. So every data is represented as a tensor. It's a multi-dimensional vector, and that's why the NumPy in Python was developed. The n-dimensional array in NumPy, or the tensor in Torch and PyTorch, is developed. So that represents. You want to take a 5 minutes break? All of you want to take a. Oh, you want to take? Sorry, I got confused. Yeah, let me complete this. So tensors is the math of the data. Okay, and that's how you represent whether how vectors are, matrices are. As I said, the image, each pixel is a number between 0 to 55, and that's how it finally looks like. It's a matrix. And when it's a colored image, it will be a three-dimensional matrix. Now imagine if it's a video. If it's a video, then that's three-dimensional matrix with another time and dimension. That's a four-dimensional matrix. So it's called a tensor, right? So a tensor is everything. A stock market data is a tensor. Language data is tensor. Okay, language data. Let's say each word is a n-dimensional array. N-dimensional vector, and there is a time component to it that each word is coming. So it's a two-dimension, you can say. Okay, that's it. So as I said, how is language data a tensor? It's in that format. Now, what I said about this semantic and the positional, this has been well studied in the history and the literature of language, that it's named under the, if you want to read more about it, let's say you want to build a career in language modeling, so you should read more about the fundamental history of how language was done, how modeling was done before this AI stuff. And that actually, to be honest, AI has not changed much, just the computational part has increased, and hence the result. So statistical uh, mechanics, or statistical semantics, sorry, is the positional information, that how two words, like we will talk more about it. So essentially it means by how a word is characterized by the company it keeps, the positional connection to one another. Okay, just like, for example, if I'm not wrong, you always come after, or there is something. So after Q, always U comes, probably, right? I'm not sure if I remember this relationship from language. So after Q, always U comes, okay? Or after any noun, a verb ideally should come. Not a verb always, but yes. But I hope you're getting what I'm saying here. That a word is characterized by the company it keeps. Okay, that's a statistical mechanics and a semantics, and this has been well studied in history, in literature. And the distributional semantics, that similar meaning of words should be close together. This is very important, guys. Okay, that similar meanings of words should be close together. That means their cosine similarity, say image and vision, should be close together. Okay, so this is very important to remember. That means the cosine similarity should be high enough. Yes, high enough. That means the theta should be low. Okay, the cos theta should be high enough, and hence the theta should be low between two vectors. And this is exactly what is done in modeling. For example, I gave you this example of king minus man plus woman is equal to queen. Okay. So let's see. I have taken the tokenization from of BERT, and sorry, I have calculated this king minus man plus woman. And you can see naturally the king will come first, The reason being that king is the first word. In fact, not only king, but woman also comes, and woman also comes. But in between, there is also a queen, which tells you that it's exactly probably doing what it's doing. And if you see token similar to king, it's queen, kings, prince, emperor. So similar words are together. Now the similarity can be many-fold. Queen and king similarity is because they have the royalty thing together and they have the high stature. King and emperor relationship between maybe means the same thing. So this when you say when these vectors, the vectors represent both positional and distributional semantics, like statistical and distributional semantics, both information together. Okay. So we want to make sure that this vector, the representation, contains both of this information. And that is very evident from this, that it's learning. So these are the learned vector representation after training an AI model that you are seeing here. The model in this case is BERT. All of it makes sense, everyone? Any questions till now? So we'll take a 5 minutes break as suggested, and we will move on to the next part of what is language model. In that 5 minutes, you can feel free to ask me any questions, and I would be happy to help you. So any questions you have? Okay, people have no questions. They want to rest.
Yeah, so shall we take for 5 minutes break or continue?
No. We will be again starting from let's say after 5 minutes.
Okay, no problem. Okay.
Yeah,
So I
people can
will.
ask.
Okay,
Sorry.
okay. No, so the question and the session will be going on, right?
Yeah, people can feel free to ask questions. They should ask questions because
Okay, then I
they
will not pause the recording actually.
don't pause the recording. Yes.
Okay, no problem. Okay.
Yeah, people. I mean, I am sure the question should come like automatically. I think it's like more of discussion happening
Yeah,
while,
both way interaction. It will be better. Exactly. Yeah.
I have a
because
question.
people will. Yes, go ahead, Shubhranshu. Yes.
So this relationships, this weights when you are defining it. So this weights are, is that standard way of defining how much weightage you will give, or is the based on the modeler who is deciding the weights?
Good question. So previously these were learned. These were pre-decided, but now these weights, this rather not weights, human vectors, right, Shubhranshu?
Yeah, but I mean, let's say king and queen. What will be the projections? That's you're defining,
Yeah,
right?
okay. So those are learned right now in this. We will see while we discuss the GPT kind of architecture. Those are learned itself by the entire model while training huge number of data. That's the usefulness of large. It automatically learns those representations. Make sense, Shubhranshu?
No, that's you are doing, let's say, self-supervised way. When you are doing supervised way, in that sense, let's say you are defining like the matrix you are can during modeling we are not filling those matrices like you are written x-axis and y-axis, right? Srijit loves to do math. So that matrix is how you can fill that. I mean, how will be this matrix will be filled up, or it will come through the analysis mod.
It will come through the modeling.
It
So
comes
we
through
will
the model.
set up. Yeah, that's the whole idea of how language modeling is done. Yes. So okay, so I want to talk about that. This is equivalent to attention, and we will see a few more examples about this. But there are two understanding. One is the first step. Let's not make them together. First step is there is a vector representation, Shubhranshu. Okay.
Okay.
And then this attention and other things come up naturally. So this vector representation is learned using modeling. They are also sometimes predefined. Okay. But in this whatever language modeling models you see in large LLMs, in those cases they are pre-trained. But there are also cases where, in those cases they are learned through a large amount of data. Okay. It can be done also in supervised learning because it's data, it's learning. But It can also be done in supervised learning. That's not a problem at all. I don't see any problem there. But previously, when there was not so much data, it can also be predefined based on.
Okay.
I mean, now the world has changed, and after learning only those pre-trained weights can be used for other tasks. Pre-trained
Okay.
vectors, sorry. Okay.
Like when
So
you think, I mean, when I heard that key, that OpenAI has created data sets of, I mean, created those created data sets, then they have trained for the large model. So I understood that key, those when they created data set, that means they have created those matrix values
vectors.
individually.
No,
No.
no, no, no. So when they create the data set, okay. So okay. So this is a suggestion to all of you. You should watch this person's. See, first of all, my research is not language. Okay. I work on vision. I work on images. But the reason I could learn so much about not so much, but I learned significantly to understand the fundamentals is because of this person whom I'm writing in the. So he has an online YouTube channel. He has very
Hmm.
few videos, but those are 3 hours, 2 hours videos, and you should watch his videos, understand his videos, watch them repeatedly, 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 and he has discussed the very fundamentals of it. Okay, and he talks about how GPT everything. So you should watch him. Watch his videos. That's my suggestion. Mm. Now, when we say so, any data, whatever data you are creating for any modeling, that needs pre-processing, right?
Okay.
Uh, that needs a lot of pre-processing. So when they said that OpenAI create their own data set, so they took the data set from the wave, they remove certain data sets, okay,
Hmm.
which because most of the data set is garbage, most of the data set is garbage. So they remove the data set, made it so that like yeah, many data set is garbage, so you do not want to make it in put it into your training, right? That's what they meant. And then the next part is also important which was actually, to be very honest, the part before me. Um, that is the tokenization. Now,
Hmm.
after the data set, guys, the next natural question is that what will be the fundamental elements of the data set? As I
Hmm.
said, the vocabulary that can be
Yeah.
based on words, that can be based on characters, but there are different ways of tokenizing. So, tokenization definition is converting our data set, our text data set, into tokens, which are the fundamental units of
Okay.
which becomes the vocabulary. Does it make Shubhram of this?
Yeah.
So, OpenAI, as far as I remember, they use something called byte pattern encoding. So that's
Hmm.
exactly not extracting the words or part of the words. So based on um, it's not based on the semantic meaning of the tokens. Okay, it's based on
Yeah.
an algorithm, which
Algorithm.
is
Yeah.
not related at all semantics, neither position. They cut randomly a word in the middle based on the algorithm. You can see that. You can see that online. But again, that's the second step. The first step is preparation of the data set. The second step is um, let me write it down. So these are good questions. So we should use this as so we first prepare the data sets, like remove garbage data. The second is we should divide the data set into tokens. When I say tokens, is atoms of the language of vocabulary. So this becomes a vocabulary. And we will see in the language model next that uh, where this stands, why it's important. So this is the x1, x2, or xn. This is a pre-processing. So this is the step 2. The step 3 is now each of these tokens should be the embedding. Each of these tokens should be changed into a vector. Okay. Now that previously that vectors were predefined,
Hmm.
now it is trained automatically. okay, from large data. And that's what I'm showing you here. This was an example. I don't know why I started writing this here. Shoot. Yes, that's what I showed here. This is actually pre-trained. Okay. This relationship is pre-trained. That's why it's not exact.
Okay.
So, and then you model. And the modeling should contain both the position and semantic. And you will see that how each of them are taken care of. This position is actually embedded in the embedding, and both the semantics is learned. This is where the attention comes, and this is where the positional encoding comes. That's it. So you have to understand that all the AI models that you build, that you are seeing here, this is very important because I don't know like your background, all of you, but they're students, they're professionals who want to learn. So from that perspective, I believe that each AI model that you build, um, each should be related to the data set, data structure, okay, and the data meaning of that. So the ideal pipeline of building an AI model for a different data set, let's say you want to build an AI model for a different data set that you have never seen before. So you should first understand the data set and read literature about the data set. Let's say you want to build a model for protein folding. Okay, so you should understand a data set, understand what are proteins, what is the structure of proteins, and you will realize that these are represented by molecules and merged together. So how can you represent that? And you see, okay, the best mathematical data structure is graphs. Okay, the best mathematical representation or data structure representation. So what other data modeling is there? So this should be the way, rather than putting any model through that. Okay, you should think about the data set, the mathematics of the data set, read the literature of the data set, and then build and see which model can help it. If there is no such model, build a new model, okay, and then train it. So there are two components. One is understanding the data set, one is the modeling, and one is the training paradigm. These three things are very different, okay, and you should, and rather the third thing is what is very common for all of them. That's the tech part. But the science part is understanding the data set and the modeling building part. Does it make sense, all of you guys? Yes? No?
Yeah.
I
Yes,
gave a
yes,
long
sir.
answer to a short
Yeah.
question, but I hope it was helpful. Okay, is the break over, guys? I think so. Okay. All of you ready? Okay, I'm writing down this Andrej Karpathy thing. Yeah, looks pretty good. I think we are good to go from here. Okay. All of you ready for large language model? For what is language modeling, guys? You have to say yes in the comment box. I want to see how many people are not sleeping.
Yes, sir.
Okay, good, Mohan. Thank you. Okay, only 10 people are not sleeping. Very good, guys. Yeah. Oh, sorry. Are you talking about this one? Only one?
Yes.
Do you see any other screens? Yeah. Is it fine now? Is it better? I cannot hide this, unfortunately. I don't know.
Yeah, it's
I
better
did.
now.
Okay. Thank you. Okay. Thank you. So what is language model? I told you already, the language model is given a set of words. Let's say you're given this data set, x1, x2, or other. I already used the variables x1 for the vocabulary. Let's not use that. Let's say token 1, token 2, token 3, token n. So you're already given this sequence. Then the next is, what is the token n plus 1? What is the token n plus 1? Okay. What is it? So to do that, let's understand that, yes. So we want to understand the problem. So to let me revise a few things so that you do not get lost. Okay. To remind you, we already discussed that first of all, the basic stage is this, as I said, the tokens. So each vocabulary is a set of tokens. Let's say they're n, capital N tokens. There can be nothing else than this. Only possible tokens. So thanks to Shubhranshu for asking that question, that we have the first data to model and then to training. So this this data to model has its preparation and then to tokens. So I am assuming the preparation addresses happen and then we have the tokens, which are the vocabulary. And those are fixed. You cannot change that. You cannot have anything more than that. So that's basic prerequisite, guys. Let's say you're doing it for a Chinese modeling, a Chinese language modeling, okay? Or then that's it. Let's say you want to do it for Arabic. Okay, so that's the basic first step. Define the tokens, all the possible tokens. So essentially, how do you do it? It's simple. Algorithmically, you take the entire data set and then you do unique. You take the unique data set, unique of the data set. What are the unique tokens? And that gives you the vocabulary. Does it make sense, all of you? I'm doing it very slowly so that you understand and build the basics. Okay. Isn't there an option for an emoji like in Google Meet, like, yes, give a thumbs up, I am understanding? I don't, let me know if you, oh, oh, very good. Yeah, please use this. It helps me. Yeah. Very good. So the next, so is this fixed, right? It's fixed now. So what next? We want to predict. So now, let's say, let's take an example, right? We will take an example. Let's say we are using, let's say I have this following data set. I am assuming each token is just 3 characters, A, B, and C. Okay, simple, so that we remember. A, B, C, A, B, C, A, B, B, C, A, B, 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 A, C, C, C. Okay. So this is the data set D. And from this we build a vocabulary. We do see the unique A, B, C. Now what? Now, what is the problem statement here? The problem statement is, based on this data set that you are learning, this sequence of tokens is a data set. If I give you a new data set, let's say BBC, okay, the BBC News. Let's say I give this. Then what will be the next token? What is the best probable token after this? A or B or C? Which one? So it's BBC A, BBC B, or BBC C. Which one it is? So how do you model this, guys? That's what the whole problem statement is. That given a set of tokens, a sequence of tokens, not set, sorry. T1, T2, or small n, T small n, what is Tn plus 1? So what is the mathematical setup of that? How do you mathematically define? This is very important. The way to mathematically define it is the following. And that's where we use probability. How do you define it? So instead of, so what I'm defining is Tn plus 1 is nothing but a probability distribution over the tokens in the vocabulary. So ideally, this Tn plus 1 should look like, it's not a single value, it's a token, but it should be looking like a probability distribution. If you remember this diagram of, so you have A, B, C in the top, and below we will have some probability of A, probability of B, and probability of C, and which we don't know. The goal of our goal is to estimate this, get this data, the values from data, from these data. Does it make sense, all of you? Thumbs up. Any questions? Thank you, Bijit. Okay, thank you, Monday. Okay, no questions? Very good. So our goal is to, therefore, given this sequence, our goal is to find probability distribution, the probability of this Tn plus 1, given that you have this data set, or you have this past 3 tokens. Okay, what will be the next one? So let's ask a simpler question. The simpler question is, instead of these 3 tokens, if I ask, I have just A, then what will be the next? So similarly, we'll have what will be the, essentially the goal is to, therefore the goal is to find this PA, PB, and PC. Okay, so now let's see now. So language model is the task operating this. What comes next? Students open there are a lot of options. It can be books, laptop, exams. Again, so now I am doing it. So I have given an example in a very restricted space. Now imagine the English word or vocabulary is large, very large, and we have to find a probability distribution over that. Okay, so the basic idea is this: given these words, what will be the probability of the next word, where this, if that xt can be. So essentially, we have to ask what is the probability of A, what is the probability of B, and what is the probability of C. Here it's asking what is the probability of W1, what is the probability of W2, dot, 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 dot. Okay. This system that does this is called a language model. Does it make sense, all of you? All good? Yes. Give a thumbs up. Okay. So to come before this, okay, so we will come to this setup soon. Let's go to a simple. So this is the first simple language modeling that has been done. Okay, the first simple language modeling that has been done. It's called the n-gram modeling. So first I will do the 1 gram modeling, and then I will go to 2 grams, and then I will do to n-gram. Okay. And this is exactly the same modeling that Claude Shannon has used for building that mathematical framework for communications. Okay. he was the first person to do this modeling on language data. So let's see this simple example. To understand this simple example, let's do a simple example here. Let's take this data set and let's do it by hand, okay? Because that's the best way to learn. All of you should do it with me here. So here's a data set, here's the vocabulary. So the goal is, the first step is to count how many A's are there, what is the number of elements in the data set. So we want to count simple probability of A. How many A's are there, how many B's are there, how many C's are there? Can someone count? Can someone count? So let's mark it. Mark the A. Okay. The B's. And the C's. Ooh, I should have another one. Where's the green one? Good. Okay. So now count the number of A's, B's, and C's, guys. Anyone? How many A's are there? Okay. 6 C's. Yes. 9 A's, 7 B's, and 6 C's. Very good, guys. So how many total elements are there? 22. So now you can see a very simple probability distribution of A, B, and C, where understand it's how based on how many A's are there, how many B's are there, how many C's are there. No relationship is here. Understand this. A PA can be easily defined as 9 by 22, PB can be defined as 7 by 22, and PC can be defined as 6 by 22, right? There is a very easy modeling. It's also a language model. It's also a language model, right? Because I can say that after this is the best probability that I know. It's language model. So the goal is to build this probability distribution based on past data. Now if I say that all of you got this, guys, can you give a thumbs up? This is a language model. Does it make sense? It's the simplest possible language model, I would say. Simplest possible language model. Okay. But now if I would say that what is the probability that of A given A, that you already know A has come. What is the probability of B given A? What is the probability of C given A? This is same as what is the probability of A given B? And what is the probability of A given C in this very specific case? And same goes here. If I say that, okay, I have observed the character B, what will be the next word? Next character. Let me write it down. So observe this one. Whatever I observe in this case, that given, if I observed A, B, or C, the probability is the same, right? Does it make sense? Whatever I observe here, the probability of B is the same because these probabilities are fixed. what I want to observe here, the probability of C should be same. In this very specific model, in this very specific model. Does it make sense, all of you? Can you say yes or no? Or, give a thumbs up? Is very important to go to the next step? But do we want this? We want this to be more. We want this to be more fundamental. We want this to be more detailed. We want to actually understand how the relationship happens. So there is no relationship here. Right? So this is what this model is of now. The simplest possible model is called 1-gram modeling. In this it's a single token distribution. I'm assuming that all these A's, B's are independent. I'm assuming all these A's, B's are independent. They have no relationship with one another. But this is not true. So therefore, the next part, so I have just shown an example here, okay? But by doing hand, I realize it's better. So I whatever you see here is an extended version of that, what I'm doing by hand. Since I have more time. Last time actually I had 2 hours, so that's why. So this is the simplest possible modeling. Okay. And therefore, let's do 2-gram modeling now. Let's do a harder one. Yes. Let's take the same data set and let's do a 2-gram modeling, which will come here. So what is 2-gram modeling? Probably you have guessed it by now. It's modeling pairs at a time. Okay, so we'll draw a matrix like this. This is previous word, this is next or character. Here's A, B, C. Here is A, B, C. It's a Markov chain, to be very precise. The same Markov chain is also used for stock market prediction. The same Markov chain is used everywhere, actually, to be honest. So, okay, so let's understand. Let's calculate now that after how many A's A occurred. After, like, given A has occurred. After that, how many A's have occurred, how many B's have occurred, and how many C's have occurred. Okay. So let's now rewrite this to know this, to understand this, we have to divide it into therefore A, B, B, C, C, A, A, right? A, B, B, C. So I'm here. Remind me if I'm missing something. C, A. Ideally, you should also be doing this by hand. A, B, B, C, C, A, A, B, 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 again B, B, then B, A. Yeah. Let me complete, then tell me. A, 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 C, 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 and then C, C. So there are 22 here. Ideally, here it will be 21. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So Venkata is right. So there is one BB missing. So tell me where it is. AB, BC, CA, AA, AB, BC.
So after fifth AB, there should be BB and then it is BC.
Oh, very good. Thank you.
Thank you, sir.
It's BB here. Very good. So Let's now calculate it. We are at the perfect place. So let's make different. So let's make one for AB. Let's make AB. We need AB, AA. So let's make it AB first. Oh, that's a lot of AB actually. Let's now make it for AA. 1, 2, 3. Am I missing? AC, AC, AC1. Yes. Let's make for BC. BC. 4 A's, you are right. Thank you. For BC, 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 BC. Okay. Another BC. Let's make it for BB. Let's make a yellow one. BB. Okay, let's make it for too many colors. CA. Okay. Light blue is for PA. And there's another, let's say purple for CC. Very good. Okay, so let's now count. After A, how many AAs are there? 1, 2, 3, 4. After A, how many AB, like B's are ABs? 1, 2, 3, 4 again. After A, how many C's are there? Say AC. Is in AC? Yeah, only one. Yeah, he is in AC. So let's mark it. It's like tally marking. AB is done. 4 AB. Yeah, tally marking is the best. 4 AB. Now 4 AA. 1 AC. Okay. Now BA. 1. BB. 1, 2, 3. BC. 1, 2, 3. Very good. Thank you for joining in this. CA. 1, 2, 3. CB. There is no CB. Very good. CC is 2. So let's now check if all of it's correct. Like one way to check is sum it up. So 8, 9, 10, 13, 16, 19, 21. Yes. So ideally it should be 21. So it's 21. Now so you have now got probability of A given A to be, understand, this is a bit it's a bit complicated in the sense that it's a bit, you have to understand this. You have to understand what is the probability of A given A. Probability of A given A here is A and then A happens. But out of A, only 9 is possible. Similarly, here 7 is possible. Similarly, 5 is possible. So probability of A given A is not 4 by 21. It will be 4 by all the options that are available after A. So options are available is 9. So it will be 4 by 9. It's called conditional probability. Okay? So does it make sense, all of you? Give a thumbs up. Probability of B given A, sorry. Similarly, here will be 4 by 9. And probability of C given A will be 1 by 9. It's not 1 by 21, 4 by 29, and 4 by 21. So this gives you that a token distribution, therefore. Probability of A given A, B given A, and C given A gives you a token distribution. Exactly the same language model. given a set of tokens, what will be the probability of the next tokens? What is the probability of A given A, B given A, and C given A? Because we have only observed A right now. It will change if you observe something different. So this modeling is more enhanced. It contains the positional information actually. There is no semantic information here because A, B, C are arbitrary. So, but it contains positional information, right? Does it make sense, all of you? Can you give a thumbs up? All good with everyone? Very good. So this is what is called 2-gram modeling. Similarly, I am not going to show that to you again now. Similarly, we can do n-gram modeling. Okay? We can do n-gram modeling in the sense that we can now just take A, we can now take A, B, C. Okay? Like this. So you can do an exercise A, B, C, B, C, A, C, A, and then you can have this A, B. So you can have this long A, B, AC, BA, BB, BC. Okay? CA, CB, CC. And then here it is next and previous. It is A, B, and C. And again, you can do that. And then you find out probability of A given A, probability of B given A, or whatever, probability of C given A. And you do the same. Find it out and then divide by the sum here. So this is called 3-gram. This is called n-gram or 2-gram. This is called 1-gram. So this, if you keep on doing this, this tells you this n-gram modeling, simple n-gram modeling. Okay. So there are many ways. So these are exercises. You should read this up. I'm just explained to you by examples what it means. But this notes is available to you. You can read this up, and yeah, it will help you. So this is what the mathematics, whatever I have done by example, here the mathematics is written. Okay, probability of W1 this. So essentially you are counting. If you observe this very carefully, you are counting how many AAAs happen together, divide by total how many AAs are there. So it's this. How many, so probability of Wi given Wi minus 1 comma Wi times, like Wi, these two are happening right now. And you have to predict this. Essentially, it's essentially is nothing but how many count of how many such all the 3 tokens together have happened, divided by total number of these 2 tokens. Does it make sense? All of you? The general mathematical framework. Good. Yeah. So you can see this code, implement this code by your hand and have a better understanding after this. I do not want. Yes. So let's not go into detailed math like this. It will take time if you do not know probability distribution. So I will leave this to you for, so if you want to learn information theory and probability distribution, this is very important. Understanding conditional probability is very important. Okay. Because you understand the n-gram modeling here. It's nothing but conditional probability, simple conditional probability. That's not the goal of this discussion today, but this is notes available for you. Okay. So now how do you evaluate a language model? Okay. So how do you evaluate a language model? First, you have just like basic machine learning, you have this train, validation, and test dataset setup. You take a dataset, you divide this into this train, test, and setup, and then you will have an evaluation metric. And you will see that the evaluation metric is higher, is doing good in test. You build the model using train and validation, and then you see how it's working well on test. Okay, that's how you evaluate, right? All of you are aware of this, guys? That's how this is the basic machine learning. All of you are good with this, guys? You know this, right? Okay. So yeah, if you do not know this, please write the basics of machine learning, how to build the data set, how to do evaluation, how to do training, and that will be helping you. So this is basic machine learning. And so now the thing is that specifically for each data set, there should be a different evaluation metric. Okay. In this case, it's very it's not good to have just measure accuracy. Um, yes, because the number of tokens, so you will see that the number of tokens matter here. Okay. And we should focus on that. For example, in this case, we define something called perplexity. So how is that defined? It's defined as, if you remember, because understand that we should understand that we should have, how can I explain this to you? The probability is very important, what I'm saying. Okay, exactly, not that output. The probability is, what I'm saying is that you have to measure in terms of probability, not exact hard 0 1 output, that okay, this has come or not, this has come. Yeah, this is the way to do it. The reason being, let's say, this is to like also make sure that let's say you ideally would have A, but the probability of A is 55 and probability of probability of A is 49 and probability of B is 50. That's why you choose B, because you choose the maximum. If you want a hard output, what do you choose? Let's say if you have this probability here, you choose the one that is the highest, right, for the next prediction. That's how it's the next word is generated using ChatGPT. This, whatever is the highest, that is predicted. Okay. There are other details too, let's not go into that. So if it is done, then the performance can hard. So let's say A is 49, B is 50, and C is 1. But you choose the hard output, so you get B output, and hence accuracy becomes 0. But you don't take into account that the probability of A was also high, right? So that's why the perplexity should be defined, the evaluation should be defined based on probability, not based on just hard accuracy. Does it make sense, guys? All of you, can you give a thumbs up? This is very important. All of you. The way to evaluate a model is to define by probabilities, not hard 0 1 accuracy output. This is very, very important to understand. Now, what do you want? You want the probability to be high, right? You want the probability to be high enough, as high as possible. So now, given this test data set, W1, W2, these are the new words to be predicted. Okay. These are the new words to be predicted. So you want, what do you want? Can someone tell me? You want the probabilities to be high, right? So what is meant by the probability here? The ideally, okay, this is a bit of a sketch here, so please be a bit careful. Let's take this case. So let's say the test data set in your case is ABA. This is a test data set based on the example that we were doing. So we want probability of A But understand now, we want the probability of A to be high. But do we want probability just of B to be high? No, but because we have already predicted A. So ideally, it should be probability of B given A to be high. And finally, probability of A given AB, this to be high. In fact, if you multiply them together, so that's why you need to read about joint distribution of probability, which is a prerequisite for conditional distribution. It will turn out that it's essentially taking I am getting A at this, A, B, and A. What is the probability of all of them, the entire sequence together? Probability of the entire sequence together. This is equivalent to probability of first A times probability of B given A times probability of A given B. And you calculate them individually. Because each of them now becomes a sequence of each of them now becomes a language model output. This is not a language model output. This each of the individual is the language model output. So you use this in this framework. So you have a language model trained. Now you find these probabilities based on what you're, because the model is outputting a probability, not hard output. Understand this very carefully. It's predicting a probability. So now you multiply these probabilities to get this final joint or probability of all the entire sequence coming together. Okay, all of you understood how you're generating this entire sequence. You first generate A, and then now you generate A. Now then, given that you generate B. Now you have generated A and B. Then given that you're generating A, you're finding the probabilities of all of this. Does it make sense, everyone? Yes or no? Give a thumbs up. This is very important to understand why it's happening. This is very, very important, very fundamental. Okay. So now we get this probability and we want this probability to be as high as possible, right? And the perplexity should be low. We want it to be low. So hence we divide it by this. So since it's the product of n numbers, understand this, since it's the product of n numbers, and these are all probabilities, the value should be very low, and that can give us wrong information. The value will automatically become low if it's a probability of high number of small numbers less than 1, right? Because any number a to the power n, if a is less than 1 modulus of a and n is high, this goes to 0. You know that limit n tends to 0, n tends to infinity, a to the power n, if mod of n is 0, right? So in each of the probabilities are less than 1. So if you have high number of such outputs in the test data set, which usually it is, this will go to 0. And you may think, oh, it's working really well. So we need to somehow normalize it, somehow increase it. And that's why since it's a product, how to take a mean of a product by geometric mean. So we take the geometric mean over here. Nth root of the product of n numbers. P1, P2 dot Pn. So that it doesn't give us false information. See, I took a lot of time to explain this because you need to understand why each and every point of the term, aspect of the term is very important. Why root is there? What is exactly does it mean? What is the product? I mean, to explain that probability, why the root is there, I have to distribute this probability of W1, W2 into product of these n numbers. Otherwise, you would not understand the nth root of this product makes sense at all. So this is the geometric mean. Naturally. Does it make sense, all of you? Yes or no? Do you fully understand now that how perplexity is normalized, how perplexity is calculated, and why perplexity is calculated? Or the why, what, and how are very important. And ideally, if it's 0, if it's low, that means it's the best. Sorry, yeah. If it's low, that means it's the best. Sorry, am I? Yeah, if it's low, understand the lowest value is what? Can someone tell me the lowest value? What will be the lowest value? What will be the lowest value? Anyone? It's not 0. There's a what will the lowest value of perplexity? 1. Very good. So the lowest value is 1. Very good, Bunty. And the maximum is infinity. So we want, ideally, it should be 1. But it's as close as 1 it can be. So that's it. Yes. Does it make sense, all of you? Any questions? So this is the basic idea of language model. Now we are slowly moving to large language model because we will be talking about neural networks. Okay. So we are right on time. Another hour is left, and the rest of the discussion will be about large language model, the GPT structure, the neural network structure, and how it is trained. Okay. But what we have successfully discussed what is language and what is language model. Are all of you, do you have any questions? That's the main part. Yes, Bante.
So I request you to kindly, if you could go back to the previous slide where perplexity was discussed. Yeah. Yeah, on the text, the printed text one. Yeah. So if you could kindly, the printed text part,
Oh,
if you could kindly explain the transition from the left-hand expression of perplexity, the left side expression of perplexity, the right side expression of perplexity, right? On the left
that's
side,
what I discussed here.
yeah, so I
Prob-
probably missed that part. I'm requesting you to kindly
Okay,
repeat that.
sure. Okay. Yes. So ideally, we want that probability of all the outputs. I'm taking an example A, B, A here. This is the test data set. Okay, Bunty. Ideally, it should be that all of them together should give the best result. But that's not how language model works. The language model works sequentially. So it turns out that you can use conditional probability. It turns out that this is probability nothing but, so you can think of this in this way: A, B, and A. So we want to find the probability of A, B, and A. So first you find the probability of A, then you find probability of B, given that already you have A. So first you go to A and then you go to B. That's what it means essentially. And here, essentially, it means that probability of A given, you already know it's A, it's coming through A and B.
Yes, so this sequence of conditional probability is what was understood, but in the expression that is given above, that can we just presume, okay, there is a multiplication right in front.
Oh, I mean,
Okay.
yeah, it's a
Yeah,
generalization of.
then it makes sense. Okay, so now it is clear. Yeah. Okay, thank you so much.
Sure. It's
Yeah.
so I just wanted to make it. Yeah, you're right. I should have explained this, but essentially, it's like a product of this conditional
Yeah, the
probabilities.
product is what I was missing earlier, but now it's clear. Yeah. Okay. Thank you so much.
Yeah, very good question, Bunty. Glad you are thinking. It's very important. Any other questions?
So in this modeling process, so basically, so where the physics comes, like last we were discussing that the physics will be important. So where the physics comes, basically any data we could present the next tokens, right? So where the physics coming into the picture?
Physics.
Yeah, I mean in this modeling, so it's a if you predicting of the next tokens, right? You are calculating the, I mean, what is the individual subject's knowledge is coming into the picture. Before starting of the sessions, you told, right, that the different physics subjects understanding of this particular data sets makes helps in the modeling. So how it helps in the modeling, that I wanted to know
So
clearly.
yeah. So as I said here, probably you're referring to this. So after this training, when you're testing, the evaluation also makes sense. So whatever you're doing here is exactly the same of sequential data. Like the language has a sequential data. So this perplexity is not used in computer vision. It doesn't make sense there because there's no sequential aspect there, right? With time. But this perplexity is a very good idea for stock market analysis. because there's a sequential analysis. But again, they are yes, yeah, that's also possible. So, but there is no such that in stock market the value is not discrete in nature. It's continuous. It can take any value. So you have to adjust perplexity a bit there because there's no concept. Yeah, that's a bit important there. So, but the stock market does this sequential data naturally demands perplexity because you are doing the modeling based on what information you have in the past, right?
No, but that's itself is a data, right? I mean, is that how the data? I mean, underlying physics behind the data is considered anywhere? That's not that important, right? I mean, you can give me any sets of data without knowing which field it comes. It could be modeled, right?
Yeah, no. So, I mean, for example, as I said, the perplexity cannot be used to evaluate or whatever the methods I have discussed. This token idea, I mean, yes, it is done now in vision, but it's not natural to the vision data, or it's this perplexity is not natural to vision data. Do you understand what I'm saying? So this modeling framework, this idea comes from the very fact it's language, and language is nothing but the modeling is nothing but probability of the next token, and it's discrete, okay, from the previous ones. Does it make sense, Shubhranshu?
Okay, fine. Yeah.
No, I mean, please clarify
No,
it.
yeah. I mean, it's we are talking in the text. I mean, I could have understood that that once we're talking about the modeling, I think I understood that modeling there we bring the I mean, like the how the relations are built. Those physics would be embedded here. So it's in being general, right? I mean, we have a set of data, set of tokens. We are finding the next token, so that the underlying mathematics is same for all sets of data. Correct?
All sets of language data, you mean?
Yeah, I mean all sets of data. I mean, if you present into the vectors, let's say A, B, C, whatever way, then how we projecting the next tokens, it's the same for any sets of data, right? I mean, here we are not building any physics into the picture, right? Like, okay, per history sets of data, it will be look different. For some another sets of data will be different. That is still not come yet, right? In the modeling process. That's what I mean.
Oh,
I
I mean, in the n-gram modeling, not yet.
not
But in
yet.
the large language model I will discuss next, that will come. In the
Okay.
n-gram modeling, only the positional information has come.
Only the position information is coming. Yeah, that's the part. Yeah,
Yeah, okay, I understand your point of view. So now we are going to the next part, that is the neural language modeling and training of this with large amount of data. Before that, any questions, guys? Any question? Okay. Do you need a break or do you want to continue? Thumbs up for what, Shondip? Okay. Shondip wants a break. What about others? Because we don't have much time left. Do you want to continue? If two people say continue, I will continue. Okay, one people has said continue. What about others? Okay, very good. Let's continue. So we have understood that in n-gram modeling, the position makes sense, right? So how can we use the semantic information? And that's exactly where the attention mechanism solve this distributional semantics, the semantic information problem. So let's understand that how. To tell you that, let me drink some water and explain that. So what happens? You have already seen the data set. So each data set is, let's say this is a token data set. Let's say the data set is D1, D2, DK. This is the data set. I'm doing it generally now. Okay. The first step is in the neural language modeling. See, I have made an entire 2 hours lecture. So I have made this large language model course, which people like on YouTube for free. So feel free to go back and watch that. Okay. Again. So all the videos are available. The previous iteration of this was also available, but I think I am discussing in more details, more depth, more understanding, so that so it will be helpful for all. So this each of these tokens now. Yeah, I will. Okay. Let me share that so that I don't forget. Yeah, I will ask Bidisha to also share it with you. Yeah, let's do that after the class. Okay. Yeah, let's focus on this right now. So each of the data set now internally is converted to a vector. Let's call it embedding 1, embedding 2, embedding k. And what is done is this. In neural networks, this is very important to understand how neural network works. The neural networks is inspired by the brain. Okay. So if you consider the brain, this is I. The information comes here. Let's talk about logical like image information. The information comes here. It directly goes visual cortex. There are multiple V1, V2, V3. And then it divides into 2. So what happens here is an information comes. It is presented through different layers of information. Layer 1. Layer 2 is used with the output. It's called hierarchical data, like hierarchical feature extraction. This is how neural networks work. This is very important again. And then layer 2 and keeps on going. Layer 3 and then whatever is the final output. So you can think of, this is inspired by the brain, by the way. What happens in neural network? You're already being taught neural network. But in neural networks, whether it's vision or anything, this is the same structure, guys. In MLP or anything, it starts with, understand this very carefully, it will answer all of your doubts, most of your doubts. Shubhranshu also has some doubts on how modeling. So if you are building a neural network, this is how you should think. First, you have an X, this is the input, and your goal is the output Y. Whatever is the output. The output can be the emotions, the output can be a different language. In vision, the output can be it's a cat or a dog, or the output can be from blurry image to a sharp, a non-unblurred image, with high quality image. So whatever is the output, that is Y, and there's an input X. So what is done here is through a sequence of steps, a mathematical operation, let's call it F1, we get X1, which is also the hidden layer. So let's understand this. There's a hidden layer, H1, and this is, let's call it F1. It's doing a function. And then we get the X1, the transformed output. Then there's another hidden layer, H2. And then we get, this is this. Because if you do not understand neural networks, you will not understand how exactly it's happening via the neural language modeling. Okay. Then X2. Then H3. This is the third function. So this output are being processed. And then you get the final layer, and then H4 or not H, let's say L layers, F of L. So you can represent this Y as, or rather Y hat. And then what happens is there is a loss function between them and the actual Y that you want to minimize using gradient descent. All of this gradient descent, all those things are briefly discussed in the neural networks, guys. Can you give a thumbs up? In the previous sessions? Very good. Very good. Okay. So that loss is being minimized. So all of you understood this structure? Yes or no? Can you say yes or no? Then I can move on. Okay. So y hat is, so let me write it mathematically so that you understand. First, x, then f1 of x has been applied on that, and on that f2 of x has been applied. This is x1, by the way, and then f2 is been applied, and this is x2, and it's happening a composition of functions. FL. This is exactly the output. Simple. So the most important thing is this hierarchy, is this sequential step processing, it's happening. This is a technology, it's a totally different technology inspired by the brain. I believe it's more important than the perceptron model aspect, that the hierarchy, the depth. This is so important, I'm telling you. This is the single most important criteria of neural networks that can process up till depth. And the beauty is that there's a mathematical proof that you can make it arbitrary depth and can approximate a function. Okay, so this is the beauty of it, guys. And this this has a more enhanced feature representation. Just a small detour so that you understand what this depth do. So I did a small experiment. I did an experiment of, I had this data set. So I generated a circular data set. So outside circle is black and inside circle is red. So there are two levels. And I wanted a neural network. I gave this data to neural network. Is x comma y data, x comma y. The x1, x2 is the x, and the y is the level. Okay, red or black. And I made a neural network train this. So I had two layers. X, which is the x1, x2, and I want to train. So it's linear layer, just weight and nonlinearity. Weight, nonlinearity. And what I found out was very interesting, and I want to tell you that is what happens is the hierarchy happening. What exactly is the model learning? It turns out that the first layer, the model is learning the lines that are important, like this. And the second layer, the model is learning these individual lines individually. And the second layer, the model is learning that which side of the line you should look at. For example, you should look at this side, you should look at this side, you should look at this side, this side, this side. And that you should look all of them together. So that's a logical operation of AND gate. This is what the model is learning. You can do the experiment to yourself. So you can see that the lines is the level 1 feature, and this hierarchy of combination of these lines is a level 2 feature. So this is what I mean by hierarchy. Does it make all of sense now? Like, at least understand that what does hierarchy mean in neural networks? Hierarchy means this combination of features that you have learned from the previous layer. Can you give a thumbs up all of it? Does it make sense? What is hierarchy? This is very important because all of this concept will be used as I explain the neural modeling. Okay. So each of this information is used for the next year. Okay. I think this is enough. Based on this, let me explain how language modeling is done. See how these tokens, understand this very carefully. you have this tokens X, let's say token T, a word. The word naturally, okay, one more thing is in this, so this is also what Shubhranshu, it's response Shubhranshu's doubt, that how are these functions, these layers defined? These layers are defined. These are the only things where you can do it differently for different data sets. These layers are different for different data sets. For example, in convolutional neural network, for images, these layers are convolutions. For graphical neural network, these layers are graph-based. Okay, graph convolution. For large language model, these layers are made up of, so these layers are data specific. Weights structure. In images, it's convolution. In language, it's attention. In GNN, graphical neural network, graphs or social network data, it's graph convolution, or protein data, it's a network data, graph convolution. So these are the layers made up of. MLP is for tabular data. Multi-layer perceptron. Does it make sense? This is also very important. Yes or no? Any questions till this point of time? Any questions? Okay. So now imagine now I
what
will
is
explain
MLP, sir?
multi-layer perceptron.
Multi-layer?
The same neural network that has been done, like what has been done in the first session, probably. Like this.
Okay.
Yeah,
Thank you.
sure. In language. Now language layer, I would call it. The language layer, you have a token. Let's say a word like ideas. It's a word. The first step is to convert this token into a vector. But a token doesn't make sense individually, because it will learn? It will not learn anything with a single token, right? So a token singularly never come here. That's the first step. Unlike many of them, a token singularly doesn't come here. A token comes with something called a batch of tokens. Deep learning methods, principles, a batch of tokens. It can be, let's say, 32 words, let's say. Batch. So again, you can go back. I have 2 courses, free courses on my YouTube. One is deep learning course, full deep learning from scratch, and full language, whatever I am teaching. It's an extended version, like 9 hours or 10 hours version of that. You can go back and watch that. No need to just watch mine. You cannot watch that. You can watch Andrej Karpathy's large language model, because I have learned from that person. So you will learn, probably will get better information from there. But if you think that you enjoy, and since I have talked about this a lot with you in these 3 hours, so you may be aware of how I teach. That can help you in your learning journey. That's it. So you may choose that and choose that path, and I will share this with you. Okay. Now, after the discussion. So you have a batch. So this why batch, all these things are mentioned in the deep learning, which I do not have the time or luxury of the resource to explain right now, even though I would love to explain everything and teach you everything from scratch. So you have this batch of tokens. So essentially it's this T1, T2, these tokens that is coming to you. These tokens are, again, these words, you can think of it. The goal is to learn the representation of these tokens. So you have this T1, T2, T3, let's say, TB. This is coming to you. Okay, understand this very, very carefully, guys. So the first step is to transform each of them, so there's a function, into a vector. Each of them should be turned into a vector. So that's question number 1. Let's call this E. So that's the first question. That what is E? So let's name it E1, E2, E3 dot EB. What are these vectors? Again, these are learnable. Understand, these are learnable. Learnable with data. But the representation should be proper, right? These are embeddings. Yes, you are right. These are embeddings. Thank you, Reddy. Dhiraj. These are called embeddings. Yes. But what happens after that? That's the first step. And then the layers come up. Layer 1, layer 2, layer 3, dot, dot, dot. And what will be the output of the layer? The output of the layer will be, if you're doing language modeling, can someone tell me? What will be the output of the layer?
Attention.
No. What is the whole idea of language modeling?
Prediction of
Why?
Sorry.
Why hat? Sorry.
What is the
prediction
y
of
hat here, Rahul?
oh sorry.
What is the y
Predictable
hat?
output.
What is the output here? That's the whole idea of language modeling. What is the
Tokens.
output of language modeling? Sorry?
Next tokens, I mean, not to be there. Next vector tokens.
Not really. If you remember, I want you to go back and remember, actually, if you're taking notes, or if you remember, that what is the output of a language model? It's not the next token.
To predict the most closest word.
I mean, you're right, but there is a step before that.
Okay.
What was the step before that?
Mhm.
No one remembers? What is the process we get that best token?
Based on probability something you're saying.
Very good, Pankaj. Yes, it's a probability. It's a probability vector. So out of these layers, you will be getting raw numbers for each one of these. Raw numbers, let's say 0.1, 0.3, 2, whatever. 0 points, or let's say 1.1, 7.2, 9.3, minus 5.1, for let's say all of them. Let's call it L1 logits. These are called logits.
Okay.
LB minus 1 and LB. And this will be used as a softmax layer. Softmax layer is the way to convert any, I don't know if you have been taught softmax layer, but it's a way to convert any such numbers into probabilities. So P1, P2 dot PB. Now, these probabilities, you want them so now you know that in the training data set, you have this TB plus 1 in the Y. So this is the X, there is also a Y, right? The Y is, let's say, some TB plus 1. So that TB plus 1, okay, by the way, this is not over B, I'm so sorry. This is over the, such a bad handwriting. This is L1, L2, probably this is a logits over all the vectors, the entire V. And if you do softmax, you get the probabilities over all the vocabulary. V is the vocabulary, number of elements, so PV. You get the probability distribution over all the vocabulary. Now let's say TB plus 1 is, let's say, 10th one. Okay. So you will have 0, 0 everywhere. Only at the 10th position, you will have 1. And you calculate the distance between them using cross entropy loss. Specific loss. Again, for probability 2. And then this loss is minimized. So this is the y and this is the y hat. So there is no y hat. Yeah, this is the y hat. Yes. But understand, your x is collection of tokens, not just a single token. Does it make sense, all of you? Is this this modeling is very specific to language? That's what I want to mean. Does it make sense, all of you? Yes or no? Any
Yes.
questions? Can you give a thumbs up if it makes sense to you? I would like to go deep into this if you have questions. Okay. So to summarize, we have this tokens T1, T2, TB. You have the embeddings E1, E2, EB. Then you have L1, layer 1, layer 2, layer K. And then you have the probabilities. This probability is P1, P2, PV. Right? And then this is what you want. And then you have the loss function. So I always draw this diagram. Okay. Because this is very important. This is very important to think. So now so there are two questions left. One is how are the embeddings calculated? What is a layer? What does a layer consist of? These two questions are remaining. Okay. So in the next two slides, answer this question. So I have to set it up right properly. So let's go here. Okay. So all of this is not there, but let's explain. So you have a token. So the question is how is a token converted to an embedding? Question number 1. Simple. A token, initially what is done is that there is called nn.embedding. If you model a language model, you will see something called nn.embedding. Again, these are explained in details in other videos of mine. Please check them out if you have more depth questions, because I have only 30 minutes left. So nn.embedding. So what it does is, let's understand this vocabulary. As you can see, each token is an element in the vocabulary. Each token is an element in the vocabulary. Let's say a token ideas is the element of 250th element in the vocabulary. Let's say there are 10,000 words. Out of that, ideas is 250th. Okay. So it goes to the 250th index, and there's a lookup table. Essentially it's a random vector. It's a lookup table, and take that random vector in that 250th position and assign it to this. That random vector. And this assigns for every token. So every token is distinct. I mean, every token is different, but again, if two tokens are same, they should have the same embedding, right? Same starting embedding. Does it make sense, all of you? That's why it's done. Does it make sense why this ID, this index, and then a lookup table, and then this random vector is done? Because because understand that in neural networks, everything is initiated with some values, and with learning, every step, the weights are updated, and hence the individual outputs are updated. So to make sure each two same tokens are the same random initialized vector, this lookup table concept is created, and that is done by nn.embedding. Does it make sense? Yes or no? Can you give a thumbs up? Each of the step is important.
Can you once repeat that?
Yes. So let's say I love math. Okay. Full stop. I am happy. Full stop. Now, this is a token, this is a token, this is a token, full stop is a token, this is a token, this is a token, this is a token, this is a token. So let's say I has a token number of 15, math has 20, love is 25, math has 17, full stop is 1, I again is 15, M is 19, happy is 23, full stop is again 1. So you can see I and full stop are, so we should make sure that I has the same vector every single time and full stop are the same vector every single time, right? Does it make sense, Saket?
Yes.
So how do you do that? Corresponding, so there's a large table out there, okay? And that large table, you look, and those table are random vectors. So you look at, so large table means it's a matrix. Let's say 10,000 matrix, 1, 2, 3. Okay. And based on that, of course, computer scientists and engineers are not crazy enough to store that amount of memory in the in the RAM, or cache, not cache, RAM. So yeah, so they do it in a different way. Let's not go into that. They use seeds, okay, so that each vector, same vector is coming up. But you can think of it that every single time that 15 goes to the 15th index and capture that up. Okay.
Yes.
So that both the 15 has both the I has the same vector initialized. Does it make sense, all of you? Saket?
Yes, sir.
Okay. Now this will not solve the problem. This will not solve the problem because this will not just be the problem. So we are not considering into account the positional embedding. Okay. Let's say there are 3 tokens, T2, T3, this is a sequence. Or let's take this, I love math, I am happy. Full stop. I am happy. Full stop. So this embedding are created, each of the embeddings that you see. Now there are 2 kind of embeddings. One, the meaning embedding. This embedding is the first kind of embedding. This embedding that you have seen, and as you will see, these embeddings will be updated with time. All of the embeddings are initialized values, and these embeddings are updated with time. So this is, I believe, it's a context embedding. It contains the name, the understanding of the meaning of that word I. So this is the same embedding you saw when I discussed the sorry, no, just no, that's not the same embedding. I'm sorry. This is a context embedding. C6, C7, C8. But there's also this is where it becomes a position. There's also positional encoding there, which is another similar vector of the same size. Both of them are 2 vectors. So this positional embedding is not based on the I, but the position of the word. 1, 2. It's based on this, where it is 1. How it is calculated, let's not go into that. That's discussed in other videos. But we calculate a vector for that. It can be predefined. It can be learned. Okay. Both of them are there. It can be predefined. It can be learned. So each token has a context embedding and a positional embedding. Both of them are the same vector, n-dimensional. Okay. This contains the information that where it is, that is the position 1, 2, 3 in the sentence, in the batch of tokens that you have given to the model to learn, where it is standing. Okay. Here I is standing at 1. Here I is standing at 5 again. So where it is standing? So you see that these two i's become different now based on the position. But the context vector was same. The initialized context vector. And then you add them to get the final embedding. Does it make sense, guys? So this is how the positional information is embedded into the very vector of each token. Does it make sense, all of you? Yes or no? Can you give a thumbs up?
So
Any
adding in
questions?
the sense, it's a two-dimension vector, or it's adding? How adding? If you can explain what do you mean by adding? Yeah.
No. So both are n-dimensional vector. You are adding it to get another n-dimensional vector.
Okay.
Two vectors can be added to make another vector, right?
Okay. So okay. So we
Like
have a
1, 2,
question.
3 can be added to 5, 4, 6 to get 5, 7, and 9, right?
Okay. So I mean, so the first 1 to 3 is given from the library, right? I mean, it could be predefined something, right? How the human has defined where the point to the libraries. So that is there is some kind of, how to say, that depends on how we have defined those libraries. But the second one is
No,
more
those
deterministic.
are random. Those are not, there is no meaning to that. Those are initializations. As I said,
Yeah,
in deep learning, everything is initialized.
depends on the initialization, and the second one is deterministic, right? Deterministic means for a given set of context, if anyone else also defined, it will remain same, right? I mean,
Again, initialized, in some cases, in both the cases, C and P both there are modelings where both are initialized. There are modelings where both are initialized and fixed, and there are modeling where both are initialized and unfixed and trained. There are modeling where one is fixed, one is untrained, like this. Many different modelings, 4 different combinations are there, but both are updated. Yes, but yeah, does it make sense?
no. So even at the positions also could be, someone could define first one I could define someone. First one I could have given an index of 10. In some cases, I could have given up index of 30. But the second one position should be more clarity, right? It should be more deterministic,
Yes,
right?
yes, yes. So
There is a
there,
logic
so as I
behind that.
said, you're right. So the context, you cannot give a context of a vector, but what you can do is, for positions, you can go give a good initialization. You can give a good initialization and let the model learn also.
Okay. So
I mean,
my question was,
okay. So to give an idea, let's say it's all about. Okay. So to give you an idea what I mean, let's say there's a curve. There's a curve, and you want to find. So essentially, this is a loss function, and you need to find the best minimum. So if you initialize it here and then go use any algorithm to go to the minimum, it will go here. But if you initialize here, it may get stuck here, right?
okay.
So in that same sense, that initialization is very important. The same initialization, if it's good initialization, if you know it has important context, I mean context in a different way, important, you can see that yes, you can give initialization, good well-defined initializations here, then that's good. You can give it. Does it make sense? So initialization is very important. Shubhranshu.
Yeah.
Yeah,
I mean,
so I know this is a bit hard to understand, but again, there are certain intuitions that come after you do a lot of experimentations.
okay.
Do you see the point? So not everything. So I can give you analogies like this. That why. So because in this context you cannot a context vector that is related to this, because you do not know that can be learned only by the data, but you can give good
Yeah, my
initialization.
question was that how are you mixing that? That's the point, right? I mean, you could have initialized, like first one, it doesn't depend, right? You could have learned to the curve, right? Second one have a context, I mean, some value you have, still we are mixing with the older data, right? And making a single vector. So is that, I mean, how we are doing
Yeah,
it? I mean,
people have done different ways. People have done. Ideally, you want to reduce computation. You could have concatenated it, right? You could have
okay.
concatenated it, but that increases the cost of computation. And they
Mhm.
say that concatenation is this. I'm sure they have done experimentations and seen that concatenation increases the cost, but doesn't give us accuracy. So they added it. So This is where the creative part of neural network
Okay.
training comes in. But I can only give
Oh,
you intuitions that why it works, but I cannot give you how neural network works are doing it internally. Because there's certain thing knowledge that is passed on by experimentations and lot of experimentations that cannot be explained theoretically. Does it make sense, Shubhangshu?
yes, 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 yeah. Okay.
But what I can say is that if you give a good positional encoding, that works better than giving no positional encoding information.
You have no positional coordinates. Yeah. Yes.
Yeah, just because like this.
Yes.
That's good question. So you should ask questions like this. Any other doubts? Any other questions? All of you on good track? Give a thumbs up. I am asking you to give a lot of thumbs up, but I just want to make sure you're understanding. That's my duty as a teacher. So, yeah. Okay. So this is how the embeddings are created. So these embeddings are created. And one important thing is now how layers are what layers consist of. So let me go here. Ideally, they should be here. Yeah. So again, here, look at this. How are you doing? So there is this position encoding and token embedding, and both are added to get the final embedding. Okay. I don't know why the size don't match here, but ideally it should. Probably it's showing something. And this is the same D model. And the position encoding is done by this is sinusoidal curve. I have explained this in more details in other videos. Please look at that. That's not possible to explain right now. But this has a lot of very beautiful math to it. One of the most beautiful math to it is this positional encoding is only a function of n minus m. The relative positions of two tokens, not individual position. Because as I said in this example, it's very important that let's say I love math and then again I say I love math. So the relationship between I and math should not be parted because it is at 1 and it is at 3. So if I say I love math and I love math, here it's at 1 and 3 and then here it's at 5 and 7. So it should ideally be dependent on the difference 3 minus 1 and 7 minus 5, not the individual 1 and 3rd position. So the positional encoding, and that's why a new research has come up recently. That's it. That is called and based on this, it's called rope embedding, rotatory position embedding. It's a different concept, but the whole idea is that it should be ideally the position encoding's feature should be function of n minus m. The relative distance of the tokens, not the absolute token distance. Does it make sense, guys? This is also very important. These are all very important concepts that you need to know. And if you give interviews or in the future, if you do research, mostly interviews in jobs, these questions are those questions that should be asked to you. These are very fundamental questions. Okay? Doesn't make sense, guys. And you should read more about this. Yes? So the position encoding should be a function of the relative distance of tokens. How? There is a mathematical proof of this. But that should be the basic idea. That's how. So you can think of why they created this such a interesting token stuff. Because they have two conditions. One is the vector, the dimension, and another is this, it should be a function of n minus m, the relative distance. That's why they came up with sinusoidal and cosine curves, because that has a natural periodic property, the theta. That natural periodic property is there. So that periodic property helps you to build such a function of just relative distance. So like if 1 is here, 3 is here, and 5 is here, and 7 is here, so that relative distance is this distance helps you, that theta helps you. That's why sinusoidal and cosine curves. Okay, I hope you got I'm sure you didn't get the math, but you got the idea. Okay, The final is, how does attention mechanism solve this? So what is happening in attention? I have to talk a bit about that. So you have this now. Now let's draw it in this. So you have this final embedding. So this is token 1 embedding, like the after the position and both token embeddings. This is a B tokens, each has an embedding now. B embeddings. Okay. So its dimension is B cross D. So this is D-dimensional embedding for each B vectors. So this goes into the model. The model should be in such a way, that the output, this is whatever the module is, the attention module, the output is the same dimension. Essentially, this is very important to understand. Essentially, it's the same, but with the updated vector. Same dimension, B cross D, with an updated vector, or B cross D dash, but updated vector. So if it's E1, E2 here, it's E1 dash, E2 dash. But the B is same. Essentially, what it means is that somehow the embeddings are updated. That means what? The information of relationships of each token with another should be updated, because that's how the positional encoding is already done. The statistical semantics, that means the distributional semantics, the semantic information should be each updated, right? Semantic information. So whatever is happening in this module should update the semantic information. Does it make sense, guys? All of you? Yes or no? This is the most important part. Again, everything is the most important. So this is the most important part of attention, actually. Can you give a thumbs up? So the input is, so the first step is this building these vectors, and each layer is transforming this into a better embedding. From one embedding to a better embedding, from one embedding to a better embedding, each layer. So, and this each layer is making sure that the semantic information, that the relationship information is becoming more strong and validated by the data and learning process. Does it make sense, guys? This is what this attention module is doing. Now let's go into the mathematics of it. It's very simple. So what's done? Let's say I love tennis. This is the embeddings. Each of them is an embedding. I embedding this, love embedding this, tennis embedding this. Each of them are changed into a different kind of embedding is learned by the attention. These are the query, key, and value. So these are all degrees of freedom you can think of to learn the better embedding. Okay. So this query vector is another representation of this same embedding. So it's trying to give degrees of freedom to learn different vectors so that it can update the different embeddings. These are the vectors for that. So the Q and query is like this. The Q and query are two different representations of the same embeddings so that we can learn the relationship between them. So this is the relationship. So what is done here? So it's nothing but, okay, how is the key query vectors created? It's something but you multiply everything with a, so it's, if it's a B cross D, right? So this is a D cross, you can see it's a 4-dimension, it's a 4-dimension here, D cross D dash. So this is just a linear weight, linear multiplication. Everything about neural networks is linear, is 80% linear, 20% non-linear. Okay. So why it is done? Again, this matrix is just multiplied, guys. Simple stuff, matrix multiplication. This x is multiplied with this, in Python language, is wq. This is b cross d, and this is d cross d dash. So the output is b cross d dash. Here you can see 4 dimension was there, here now it becomes 3 dimension. So what it is doing? It is giving the space, the freedom to the input embeddings, the tokens, to take the other vector formations so that it can learn the relationships. And it is done for this q and k and v, 3. Now you have to understand why. The q and k will, so now once these two vectors are updated, to gather the relationship understanding between them, we will now calculate, if you remember, the pairwise relationships here. If you remember, I said that. Sorry. Where did I say that? Yeah, this one. This pairwise relationship. So what is happening here is, each of these now embeddings, now we are checking the pairwise relationship. What do we want? We want to capture that how much those two vectors are close together, right? So how are two vectors close together? By dot product. We already discussed that. So each, for example, this is 1 2 3, this is 1 2 3, different representation of those 3 words. So this I comma j, let's say this is 1 comma 3 comma 2. So this tells you the relationship between the dot product of the third and the second vectors. So each of them, so it's kind of estimating. It's a finding the relationship. And understand this, it's learning these weights. These are weights. It's learning these weights in such a way that this relationship is exactly what it should be from the data. So it's learning this, it's giving the space of freedom here, this, so that the embeddings are made in such a way so that the relationships are exactly how the data represents. Does it make sense, guys? This is super important. The intuition. Can you give a thumbs up if you understood it? I'm repeating again. The weights are trained. So this setup, this weights, you can think, why so many weights? Because these weights give you the degrees of freedom to learn the embeddings so that the relationship is exactly captured the way it should be in the data set. Makes sense, guys? Yes, no, maybe? Okay. And now the relationship is done. So what? So what does this give you, this attention score? This attention score give you, this is 1 2 3, this is 1 2 3. The first row gives you that, okay, 1 has the most probability of going from 1, so it's 0.7. Then 1 have 20% probability or relationship is 1 to 2. And then 0, this is the first row. Similarly, the second row. So it's a pairwise relationship. So there's a 70% most relationship. Like if you, so this 0.7 tells you kind of the probability after, so there's a softmax here. So it turns in the probability from each element to the next element. This tells you that how much weight, it's kind of give you the weightage. Now, what is this value doing? This is telling you the relationship. This relationship is that this is a relationship score, that how each relate to each other. But based on this relationship score, the vector should be different. So ideally here, I and tennis have no relationship because it are randomly selected 90 degree. But ideally, we want that the vectors that will be learned here should be close by, let's say 10 degree. That means close by, high cos theta. right? That's what we want, right? Yes or no? We want that if two things are occurring together and have semantic meaning, they should be close together, like king and queen should be close together, man and woman should be close together, because the human beings are royalty. Doesn't make sense. This is what we want. We want the embeddings to get updated via the relationships that they present via the data set, through the data set. So we have this relationship through this softmax. But to update this embedding, we need this value vectors. So there's another set of freedom vectors that we are learning. So what we do now is that we now get the new I vector. How? We already have this I. So how? Using this relationship, we already know that 1 is related to these vectors. Or rather, which vectors leads to 1? How much? Now, which vectors leads to 1? So this tells you, let's say, or something else, I don't know. Here, 1, 9. This shouldn't be a probability. 9. So what do? You take the linear combination of this in that corresponding proportion to get the updated I vector. So essentially, in other words, you're using this relationship and the weights to update the new embeddings. And the reason is, here you have no relationship and you ideally have more informed relationship. How do you capture that? By the cosine similarity. And that's exactly what the attention module is doing. It is just measuring the relationship so that the embeddings are updated from perpendicular to something that makes sense in the embedding space. Does it make sense, all of you? Yes? Any questions? So this is all about large language model, guys. Language model. In large language model, the entire thing that I have described is the self-supervised learning, because there is no supervision from outside here. You have a language and you're building your data set from here. So this is called the self-supervised learning. I already explained this. Yeah, so I already explained this, what happens here. So using diagrams, so you can read through it. Yeah, that's it, guys. So the whole framework that I've described here using diagrams, that how the entire learning is done. This is the framework of self-supervised learning, because the dataset is coming from the own dataset. There's no external supervision. The entire dataset is corpus is there, and you're breaking out the dataset to predict one part from the another part. So this is self-supervised learning for you guys, and that's actually comprises the large language model part 2. And for detailed discussion about how GPT is done, how GPT is created, how everything is done, I have a whole section of video on what everything is done using code. Okay, and that can surely help you. So that's all about it. I have discussed more about pre-training and stuff in the first iteration of this, but I realized that it was too fast and it was not useful. I believe it was rushing through it. So I took time initially, each 1 hour, to describe each individual component. The first for what is language, the second for what is modeling, language modeling, and third is how actually large language model, neural language modeling is trained. Okay. So that's all about it. Thank you for your time. I hope you learned something from it. So that's all about it. I will send you in the meantime, I will send you the YouTube link.
So anyone having any question left?
Yes. Thank you, Shondip. I hope it was helpful for others too. Okay.
So I
So I have
think,
given this link.
yeah,
Sorry?
continue. Yeah, continue.
Absolutely. My pleasure. So I will share also this link with you. I will be, first of all, this notes is very important. I am sure Vidisha will share this link with me, this recording, and
Yeah,
I will be
sure.
uploading this to my YouTube, and you can see what's recording again. I will publish this notes on LinkedIn, so you can also get the notes from there. And thank you for staying till the end, all of you. Thank you for your
Yeah,
time.
so I think we came to the end of Srijit's sessions as well. With this, we came to the end of today's session as well. So, on behalf of all participant and Ideas TIH, sincerely thanks to Srijit Mukherjee for sharing these valuable insights with everyone. So, thank you so much for your time. Uh, so, participants, so if you have any further questions or any queries, so you can directly approach him. I think his email ID already shared, right?
Email ID shared. I am also sharing my LinkedIn.
Okay. So by anyway, if anyone have any further queries or want to go deep into the topic, so they can directly connect him.
Yes, absolutely. Thank you for the invitation, Vidisha.
Thank
And
you. Thank you so much. I will share the recording with you.
yes, absolutely.
Okay.
All the best. Bye bye.
Bye. Thank you. Thank you, participants. So we are closing for today. Good night to all. Thank
Good
you.
night.